Hello there, geometallurgists. This is 7th of March 2020. My name's Adam, and I'm going to give you a walk through the new Cancha 1.5 feature, which allows you to measure sample distances for each block in the block model. Conceptually, this isn't super easy or intuitive to understand when you're using an actual project, so I've created this fake data set called Mount Martin, which we'll make available for download. And it's basically a very small block model with just 2 blocks wide, 1 kilometer by 500 meters. And it's got 3 domains, maybe lithology, something like that. You got 101, 102, 103. They've just been called 3 drill holes in it. Let's just have a look at the drill holes, and you can see we've manufactured some samples so that they're in these different domains. So what we're going to do is dead easy, just go to features, and as you can see here, what I've already done is populate the samples. So I can click here and say populate the samples with all the other data. You should be doing that anyway as soon as you can, anytime you're using Cancha. Try to get all the information you can onto each sample. But for this one, let's just jump into this one, which is the sample distances. So click on here first to generate the distances. And we'll just do a simple one first. We won't take any domains into account, and just hit apply. So what it's doing basically, this takes a little while if you've got a big block model, but it's going block by block and working out what the closest sample is and what the distance is for each block. So that what happens is it creates this new feature. This new feature is here in the block model, and it's called just sample distances. And if I click on that, up she comes. Now, by default, you might have something that looks like this, and as you know, that this is binning, so it's got, it just creates, like any other feature, creates these sort of limits. Not super useful. I mean, you might want to, for example, reorganize these for what you would like to see as a minimum distance, and then you could paint them A and B, whether the deposit's been covered or not. So for example, if you say, okay, we're okay with all these ones, but all this other material has a low representivity, and obviously here in the corner, we've got 500 meters or more to the nearest sample. So maybe, this area hasn't been properly sampled. Okay, so pretty intuitive. Another way to do it is to change the color scheme on the block model and do something like this. And you might look at this and say, oh, what's going on here? Clearly a mistake. Yeah, look, there's certain search algorithms that we've got the search algorithm for the sample, nearest sample tuned so that it's fast. If we were to do it rigorously for each block, then what we'd find is that it would take too long to run. And so what we're saying here is that when it's over 500, it's going to have a little bit of an error. So don't worry about it. I mean, if what you're worried about is a 500 meter distance to a sample, you've already got a problem to start with. Okay, so this one you get these sort of artifacts. But otherwise, you can see it's done a good job of knowing exactly where the samples are and how distant to each block. And if we just, for example, go to an Isosurface and let's say, show me everything that's got more than 150 meters to the nearest sample, then I can just do an Isosurface like that, and I'll see exactly that. I'll see all the material that doesn't have that, okay? So that's the simplest way of doing it, but usually we're not so interested in just global distances to samples. It's not actually that interesting. What we are interested in is the distances within a domain. So imagine this was oxide and sulfide and maybe some kind of intrusive or something like that. So it's really not useful for us to know that these blocks here are close to this sample, because this could have markedly different properties than these blocks, because these blocks are probably represented better by these samples over here, and they're a long way away. So if this was an oxide copper, for example, you would want to make sure that you had oxide copper samples near here. It really doesn't help you that you've got a copper flotation sulfide sample here, because it's really completely irrelevant when you look at the properties of a weathered zone above it. So we really want to draw attention to the fact that these are long distance here. So what we do in that case is we go back to features, sample distances, and we want to generate it, but this time we're going to use a feature from the block model. And we want to use domain. This is just this could be lithology, alteration, could be geomet, whatever there's something categoric, and we put it here, use block model feature. Before I do that, I just go back and explain, we've already seen that we've got samples that are in 103, we've got samples in 101, and samples 102. Okay, so we've already done that by using the populate samples, and now let's go back to features, and we can just run this. Disappeared. Go back, put that there, apply. So now it's not just looking for every block what the closest sample is, it's looking for the closest sample that has the same domain property projected from the block that the block has. Okay, so only samples from the same domain are taken into consideration, and when we look at that, we get a markedly different result. So here we can see that this sample here has had no effect on these. The only distances here are being taken into consideration, these ones here. So all these blocks here have impacted from here. We can see here that these samples in this domain have been right in the middle of it, and so you've got a certain distribution there. And you can see that also that even though they're not connected, it doesn't have to be continuous. This is a non-connected part of this same domain. So say you had two deposits and they both had the same domain, maybe two pits, and you had one over here and one over here, and you had a sample here. Because they're the same domain, it would take it into consideration here, that sample there. Okay, so here we can see, again, we could do this sort of thing to see how far away our closest samples are. What material needs to be sampled further. Super useful. And also, then because we've got the data, now we can start to do cool things like, for example, statistics. We could pull these different things into statistics. We don't need to do some of these things, so let's get rid of the count zeros, unique values. Okay, so now we can see that the maximum distance by domain is higher than the maximum distance, and the average is obviously a lot further. Okay, so you can see those settings. You can do your graphs. You could do this sort of. So we want to put it on this sort of graph, and we can see that, okay, we've got a bunch of samples that have less than sort of 150 meters, but then we've got a long tail where there's a whole bunch of stuff that is a lot further. And if we just do that by domain, we can see that the green domain, which is in the middle of the deposit, if I'm not mistaken, let's just put that back on there to have a look. So the green one was probably the best, and then we've got this area here and this area here, the others, which are bad. So let's go back and look at the analysis. We can see, sure enough, that the green one has got 20% of the samples, and they're all less than a couple hundred meters, more or less, distance in the blocks. Whereas, we've got almost 1,000 meters distance for the 102. Okay, so we've got full use of the data, and look at it in 3D. So now we've got here in the drilling, we've got a sample distance there. Now if we go back to logs, we can put this on here. And if we put the domain on there, domain. So here we can see that we've got a lot of distance here in this domain and not much distance here on this one. So if we, for example, we were selecting samples, we might say, okay, hey, we need to get a sample here because it's a long distance here. And here we've got these, this is well covered. Because of this sample here, we've got this covered. We don't have any samples in this area here, an average of 700 meters to the nearest sample. So we need some more samples in this area. So you could basically step through your sample. You say this drill hole's pretty well sampled. We don't need any more here, maybe a little bit here, but not too much. 250 meters the nearest one. And here we've got 700 meters the nearest one. So you can see there that, you can have this extra information on here while you're selecting samples, and you'll be able to cover that gap. So say, for example, we were to do that and say, save the sample here. And we'll be able to see that that new sample that we've got, let's put this hole in this over here. You see that? So it's a new projected sample. It's not showing up because right now we're showing the bond work index, which we don't have anything for, but if we change the, there we go, looked up the manganese. So you can see this sample here. This is from the second phase of test work, but it's been able to cover that gap there and filled a hole in our sample distribution. So without further ado, I think that's enough for now. It's a powerful new feature. As you can see, you can very quickly work out where you've got a hole in your sampling distribution and fill it by selecting new samples to cover that. I hope this has been helpful, and go ahead and give a like or add comments below if you've got any suggestions on how we can improve Cancha and add new features like this. Always love to hear from our users. Thanks for your time.